Look at a glass of water sitting on a table in ordinary daylight. Drop a pencil into it at an angle, and something happens that every person on Earth has seen, and almost no one has actually explained correctly. The pencil appears to bend at the surface of the water. Ask most people why, and you'll get the same answer you probably got in a 9th grade classroom. Light slows down when it enters water, so it bends. That answer is in almost every textbook. It's on almost every educational website. It's repeated by well-meaning teachers to hundreds of millions of students every year. And it is, at the level most people understand it, deeply misleading. Not fake, not a hoax, but a simplified shorthand for something far stranger, something that most of those textbooks never actually explain, because the real mechanism was only fully worked out in the 20th century by physicists solving one of the strangest problems in the history of science. How can something that always moves at the same absolute speed appear, in certain circumstances, to move slower? This is the case file on light, and specifically on the phrase you've heard 1,000 times without ever being told what it actually means. Light slows down in glass, in water, in diamond, in your own eyeglasses. We're going to take that phrase apart piece by piece, using the same evidence physicists use to take it apart, and by the end you'll understand something that even many science communicators get wrong. Because the true explanation isn't intuitive, it isn't simple, and it comes from one of the most rigorously tested theories in the history of physics. Start with what's actually true and beyond dispute. In a vacuum, light travels at exactly 299,792,458 meters per second. This isn't an estimate. It's not a measurement with error bars that might shift with better instruments. It is, since 1983, the literal definition of the meter, fixed by international agreement precisely because the speed of light in vacuum is understood to be a genuine constant of nature, not something that changes depending on conditions. James Clerk Maxwell showed in the 1860s that this speed falls directly out of the equations governing electricity and magnetism, meaning light isn't just fast, it's the natural speed limit at which disturbances in the electromagnetic field can propagate through empty space at all. Albert Einstein built the entire structure of special relativity in 1905 on the assumption that this number, this specific speed, is the same for every observer in the universe, no matter how they're moving. Every satellite in orbit, every GPS calculation, every particle accelerator experiment run since has confirmed that assumption to a staggering number of decimal places. So when someone tells you that light slows down inside glass, they are implicitly telling you that the fundamental constant underpinning modern physics changes depending on what room you're standing in. That should already feel like a strange claim, and it is, because it isn't quite what's happening. Here's where the story gets interesting and where most textbooks quietly stop asking questions. If you actually track an individual photon, a single quantum of light, moving through the empty space between the atoms that make up a pane of glass, that photon is moving at exactly the same speed it always moves at, 299,792,458 meters per second. The same constant, unchanged, non-negotiable. There is no gap in the physics where the photon itself gets slower while it's actually in flight through open space. This is the part that surprises almost everyone, including plenty of adults who took physics in college and were never told this explicitly. So if the individual quanta of light never slow down between atoms, why does a beam of light measurably take longer to cross a slab of glass than the equivalent distance of empty space? Why can we measure, with extremely precise instruments, that light appears to travel through diamond at less than half its vacuum speed, and through water at about 3/4 of its vacuum speed? If nothing in the underlying physics is slower, where does the missing time go? This is where we have to rewind, because the answer didn't come easily, and the scientific community spent centuries circling around versions of this question, without landing on the real mechanism. In the 1600s, Isaac Newton proposed that light was made of tiny particles, what he called corpuscles, fired out from a source and traveling in straight lines. Newton's model could explain reflection reasonably well, but it ran into serious trouble explaining refraction, the bending of light at a boundary between two materials. Newton's corpuscular theory actually predicted that light should speed up when entering a denser medium like water, the opposite of what later experiments would show. Around the same era, Christian Huygens proposed a rival idea, that light was a wave, spreading outward the way ripples spread on a pond. And Huygens' wave model predicted the opposite of Newton's guess, that light should slow down in a denser medium, not speed up. For over a century, this was essentially unresolved, an argument between two of the greatest minds of the scientific revolution. And it wasn't until 1850 when the French physicist Léon Foucault directly measured the speed of light in water using a rotating mirror apparatus that Huygens turned out to be right on this specific point. Light does slow down, in the sense of its measured group speed through a medium, exactly as wave theory predicted. Newton, remarkably, was wrong about something this basic, and it took nearly 150 years of technological development just to build an instrument precise enough to settle the argument. But confirming that light slows down as a wave doesn't yet tell you why, at the level of individual particles and atoms, that slowing actually happens. The wave picture describes the behavior beautifully with mathematics, using something called the refractive index, a number physicists label with the letter n, which tells you the ratio between light speed in vacuum and its effective speed in a given material. Water has a refractive index of about 1.33. Crown glass sits around 1.5. Diamond, famously, has a very high refractive index of about 2.4. Which is part of why diamonds sparkle the way they do, bending and separating light so dramatically. These numbers work. Engineers use them every day to design lenses, camera systems, fiber optic cables, eyeglasses, telescope optics, all built on the refractive index framework, and none of that engineering is wrong. But the refractive index is a description of an effect, not an explanation of a cause. It tells you how much light appears to slow down. It does not, on its own, tell you what is physically happening to the light while it happens. The real mechanism required quantum mechanics, and specifically it required the theory known as quantum electrodynamics, or QED, developed in the 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. Independent work that won all three men the Nobel Prize in Physics in 1965. QED is, by a wide margin, one of the most rigorously tested theories human beings have ever produced, with predictions confirmed to more decimal places of accuracy than almost any other framework in science. Feynman himself spent a great deal of effort trying to explain QED to non-specialists, most famously in a series of public lectures later published as a book called QED, The Strange Theory of Light and Matter. Precisely because he believed the true mechanism behind ordinary phenomena like refraction was so counterintuitive that most people, including most working scientists outside the field, had never actually grasped it. What Feynman described, stripped down to its essential idea, is this. Light moving through a transparent material like glass or water is not a continuous, uninterrupted journey where a single photon simply travels a little slower the whole way through. Instead, what's actually happening at the level of individual atoms is a constant, extraordinarily fast sequence of absorption and re-emission. The photon interacts with the electrons bound to the atoms in the glass. It is, in a meaningful physical sense, absorbed, and a new photon is re-emitted an instant later. That new photon travels, again, at the true vacuum speed of light through the empty space to the next atom, gets absorbed again, re-emitted again, and this chain repeats itself an immense number of times as the light crosses the material. Each one of those absorption and re-emission events introduces a tiny delay, a phase shift, because the electron doesn't simply pass the photon along instantaneously. It takes a small amount of time to respond, to oscillate, and to release a new photon. None of these individual delays are anywhere close to what you'd call a slowdown in the way a car slows down when it hits mud. There is no continuous deceleration of one persisting particle. What you get instead, mathematically, is what's called a phase delay accumulated across an enormous number of interactions. And when you average that delay across the whole beam of light and the whole slab of material, the net effect looks, from the outside, exactly like a single beam of light moving at a slower, constant speed. That's the refractive index. It isn't a description of light itself slowing down. It's a description of a statistical, emergent effect caused by billions of individual quantum absorption and re-emission events, each of which still obeys the same unbreakable vacuum speed limit for light in the brief moments it's actually in flight. This is worth sitting with, because it resolves something that would otherwise look like a contradiction in physics. If light in a medium genuinely slowed below the vacuum speed of light as a continuous particle, that would create tension with special relativity's insistence that the vacuum speed of light is an absolute, unchanging limit. But because what's really happening is repeated absorption and re-emission, with the photon always moving at full speed between those events, there's no contradiction at all. The slower speed we measure for light crossing glass is what's called the phase velocity or group velocity of the light wave as a whole, a collective emergent property of the system, not a change to the fundamental speed limit of the universe. Individual quanta never break the rule. The system, taken as a whole, appears to. Before we get to the most dramatic piece of evidence, it helps to understand why this absorption and re-emission chain doesn't just create a delay, but also explains something else people notice constantly without connecting it to this mechanism. Why a prism splits white light into a rainbow. Different colors of light correspond to different wavelengths and frequencies, and the electrons bound inside the atoms of glass respond slightly differently depending on the frequency of the photon hitting them. A higher frequency photon, toward the blue and violet end of the spectrum, interacts with those electrons a little differently than a lower frequency photon toward the red end, which means the accumulated phase delay across billions of absorption and re-emission events ends up being slightly different for each color. That difference in accumulated delay is exactly what produces a different effective refractive index for each wavelength, a phenomenon called dispersion. Violet light gets delayed a little more crossing the glass than red light does, which means it bends at a slightly sharper angle leaving the prism. And that's the entire physical basis for why sunlight fans out into a visible spectrum. It's the same mechanism responsible for the pencil appearing to bend in your water glass. Just split apart color by color so you can see the effect happening at slightly different rates simultaneously. Isaac Newton, remarkably, was the person who first demonstrated this splitting rigorously with prisms in 1666, more than 2.5 centuries before anyone had the quantum tools to explain why it actually happened at the level of individual atoms and photons. He documented the effect perfectly while being wrong about the underlying particle mechanism producing it, which is its own small lesson in how experimental observation and theoretical explanation can advance on completely different timelines. There's also a subtlety in how physicists talk about the speed of light in a medium that trips up even careful readers, and it's worth resolving directly because it's the difference between phase velocity and group velocity. Phase velocity describes how fast a single, idealized, infinite wave crest would appear to move through a material. And in some unusual materials, this number can behave in ways that look bizarre, even exceeding the vacuum speed of light in narrow, engineered circumstances, without violating any physical law. Because a pure, infinite, single-frequency wave doesn't actually carry information or energy from one point to another in a way you could use to send a message faster than light allows. Group velocity, on the other hand, describes how fast an actual pulse of light, a real signal built from a narrow range of frequencies bundled together, moves through the material. And it's the group velocity that corresponds to the practical, measurable slowing effect we've been describing. The one that governs how quickly information can actually travel down a fiber optic cable or across a lab bench. This distinction matters enormously for engineers and physicists working with lasers and telecommunications, because conflating the two can lead to genuinely wrong predictions about how fast a real signal, carrying real information, can be delivered through a real material. And it's part of why the refractive index taught in an introductory classroom is a useful approximation rather than the full physical story. There's a piece of supporting evidence for this that many people find genuinely startling once they hear it, something called Cherenkov radiation. In certain very dense transparent materials, like the water inside a nuclear reactor's cooling pool, the effective speed of light for that medium can be significantly slower than light speed in vacuum, sometimes down to around 75%. Now, particles like electrons emitted from radioactive decay in that same water can, under the right conditions, travel faster than that reduced effective light speed in the medium, even though they're still nowhere close to the true vacuum speed of light. When that happens, the electron is technically moving faster than light can move through that specific material. And the result is a faint, eerie blue glow, first properly explained by the Soviet physicist Pavel Cherenkov in the 1930s, work that later earned him a Nobel Prize as well. That blue glow, visible in photographs of research reactors, is direct visual proof that the speed of light inside a medium is not the same absolute limit as the speed of light in vacuum. It's a local, emergent ceiling created by the material itself, and particles can outrun it without breaking any fundamental law of physics, because the only truly unbreakable limit is the vacuum speed, not the medium's effective speed. So here's the moment for the reality check, because this is exactly the kind of curiosity gap this investigation exists to close. The popular claim is, light slows down in glass and water. The precise evidence-based reality is, individual photons never slow down while actually in flight between atoms. What slows down is the effective collective behavior of the light wave as it's repeatedly absorbed and re-emitted by the electrons of the material it's passing through. An emergent statistical delay that has nothing to do with any single particle actually decelerating and everything to do with an enormous number of near-instantaneous quantum interactions stacking up into a measurable time lag. The pencil in the water really does appear to bend, and the physics behind why it bends really does involve something we casually call light slowing down. But the mental picture most people carry of a photon like a swimmer wading into thick syrup and physically losing speed mid-journey is not what's happening at the level where the actual mechanism lives. It's a convenient fiction, useful for 9th grade classrooms and rough intuition, but it quietly papers over one of the more elegant discoveries in 20th century physics. It's worth asking why this matters beyond trivia, because a documentary built entirely around correcting a minor classroom shorthand would be a thin one if the correction had no real consequences. But it does have consequences, in a few different directions. The first is educational. Physics education researchers have studied for decades how deeply the simplified light slows down like a car in mud mental model gets embedded in students, and how it can actually interfere with correctly understanding more advanced topics later, including relativity itself, because students carry an unspoken assumption that the speed of light is negotiable depending on circumstances, when the entire architecture of modern physics depends on it not being negotiable in the way they imagine. The second consequence is technological. Fiber optic communication, the literal infrastructure carrying nearly all of the world's internet traffic, under oceans and across continents, depends on engineers understanding the true group velocity behavior of light in glass fibers with extreme precision, because tiny discrepancies between the naive model and the actual quantum behavior would translate into real signal timing errors across thousands of kilometers of cable. The systems that let you video call someone on the other side of the planet in near real time are built on the correct version of this story, not the simplified one. There's a related consequence in how science gets communicated to the public more broadly, beyond the classroom. Popular headlines over the years have announced, with varying degrees of accuracy, that scientists have stopped light or frozen light in laboratory experiments, most famously in slow light and stop light research conducted by physicist Line Hau and her team at Harvard in the late 1990s and early 2000s. Work that used ultra-cold clouds of sodium atoms called Bose-Einstein condensates to dramatically slow and briefly halt the group velocity of light pulses under extremely specialized conditions. Those headlines are exciting, and the underlying research is genuinely remarkable, but they can reinforce exactly the misleading mental model we've been dismantling here, if audiences come away believing individual photons themselves were literally frozen in place like a paused video, sitting motionless in space. What was actually captured, stored, and later released in those landmark experiments was information, an imprint of the light pulse's exact quantum state, held in the collective coordinated behavior of the atoms themselves, not a literal photon suspended mid-flight. The distinction sounds technical, but it's the same distinction running through this entire investigation. The emergent collective behavior of light interacting with matter can look, from a distance, like something is happening to light itself, when the deeper mechanism is happening in the matter light is interacting with. Getting this distinction right isn't pedantry. It's the difference between understanding a genuinely groundbreaking piece of quantum optics research correctly and walking away with a science fiction version of it that doesn't hold up to scrutiny. The third consequence is stranger and more current. In the last 2 decades, physicists and material scientists have built what are called metamaterials, artificially engineered structures with electromagnetic properties that don't exist in any material found in nature, including materials with a negative refractive index, something that sounds almost like science fiction, but has been demonstrated in laboratories since the early 2000s. These materials can bend light in ways that look, at first glance, like they violate ordinary optics, and researchers working on so-called transformation optics have used these principles to design experimental invisibility cloaking devices at microwave frequencies, along with slow-light photonic chips designed to deliberately hold light pulses almost stationary for computing and quantum information applications. None of this engineering would be possible if scientists were still working from the simplified textbook picture of light as a particle that just physically decelerates in a medium. It's only possible because the real quantum electrodynamic mechanism, absorption, phase delay, and re-emission across countless atomic interactions gives engineers precise control over the actual variables that create the emergent slowing effect, letting them design structures that push that effect to extremes no natural material could achieve. There's also a human dimension to this story that rarely gets told, because science history tends to remember the equations and forget the people who had to live with being wrong publicly. Newton was arguably the most influential scientist of his era, and his corpuscular theory of light dominated scientific thought for over a century, in no small part because of his enormous authority. Generations of natural philosophers built careers defending a model that later, rigorous experimentation by Foucault and others would show gave the wrong prediction on something as fundamental as which direction light bends when it slows. Huygens, meanwhile, published his wave theory of light in 1690, decades before Newton's death, and by most historical accounts was largely overshadowed during his own lifetime by Newton's reputation, only to be vindicated roughly a century and a half later by an experiment neither man lived to see. It's a reminder that even the most celebrated scientific minds in history can be wrong about mechanisms, while still contributing essential groundwork, and that being correct in science is frequently a matter of decades or centuries of patient incremental testing, not a single flash of genius settling the matter permanently. Feynman himself, in explaining QED to public audiences, was candid that the real mechanism doesn't match human intuition at all, and that accepting it requires setting aside the instinct to picture light as a tiny ball rolling through space at a variable speed, replacing that instinct with a stranger, probabilistic reality involving sums over every possible path a photon could take, a mathematical technique called the path integral formulation that Feynman himself pioneered, and which underlies the entire modern explanation for why refraction happens the way it does. In Feynman's framework, a photon traveling from a source to a destination doesn't take one single definite path the way a thrown ball does. Instead, mathematically, the photon is treated as if it explores every conceivable path simultaneously. Straight lines, curved detours, paths that seem to bend backward, each one assigned a tiny rotating arrow representing probability. And the final observed behavior of the light emerges only when all of those arrows are added together. In empty space, the vast majority of those paths cancel each other out through interference, leaving only the straight line path as the one that survives with any real probability, which is why light appears to travel in straight lines when nothing is in its way. But inside a material like glass, where photons are constantly interacting with the electrons of countless atoms, the mathematics of those probability arrows shifts, and the path that survives the cancellation isn't quite the same simple straight line anymore. It comes out bent, exactly matching the angle predicted by the refractive index, and delayed, exactly matching the emergent slowdown we've been describing. Feynman used to tell audiences that this explanation was, in his words, not a simplification for a public lecture, but the literal way physicists calculate the behavior of light professionally, down to the same equations used in serious research. It's a strange thing to sit with. The same rainbow through a prism, the same bent pencil in a water glass, both fully explained not by a photon slowing down, but by a photon effectively trying every possible route through the universe, and only the mathematically favored ones surviving to reach your eye. It's also worth remembering that this correction doesn't diminish the earlier scientists who got the surface level phenomenon right without understanding its deeper cause. Foucault's 1850 measurement remains a landmark of experimental precision, conducted with rotating mirrors spinning at carefully controlled speeds and hand-ground optics, decades before anyone had the tools to explain why his results came out the way they did. Maxwell's 1860s equations remain, unmodified, at the foundation of virtually all classical electromagnetism taught today, precisely because they correctly describe the wave behavior of light even without reference to the quantum absorption and re-emission process happening underneath. Science rarely discards earlier work when a deeper explanation arrives. It usually absorbs the earlier work as a correct description operating at one level, while explaining why that description holds true using a more fundamental layer underneath it. And the story of why light appears to slow down inside glass is one of the clearest examples of exactly that layered structure in the entire history of physics. Bringing this back to where we started, the pencil in the glass of water is real, the bending is real, the refractive index is a real, precisely measurable, endlessly useful number. And in a loose, everyday sense, it's not wrong to say light slows down, crossing from air into water or glass. What's incomplete is the unspoken picture most of us were handed in school. The idea that a photon is a small physical object cruising through space that simply loses speed the way a car loses speed entering deep sand. The evidence, going back to Foucault's 1850 experiment, formalized by Maxwell's equations in the 1860s, explained mechanistically by Einstein's early 20th century work on light quanta, and given its full, rigorous explanation by Feynman, Zwinger, and Tomonaga's quantum electrodynamics in the 1940s, tells a more precise and, frankly, more remarkable story. Light itself never breaks its own speed limit. What changes when light crosses into glass, or water, or diamond is not the photon, but the medium's relationship to the photon. An emergent collective delay created by trillions of individual, faster than any slowdown, quantum interactions between light and matter, each one obeying the same absolute vacuum speed of light that governs everything else in the universe. The next time you see a straw looking broken in a glass of water, or light splitting into a rainbow through a prism, you're not looking at light losing speed. You're looking at the visible signature of an invisible negotiation happening between photons and electrons, billions of times per second. A negotiation so fast and so precisely balanced that it recreates on a large scale something that looks exactly like a simple slowdown, without ever actually being one. That's the reframe. Not a myth completely busted, but a shorthand quietly replaced with the real mechanism underneath it. The same mechanism running the fiber optic backbone of the modern internet. The same mechanism physicists are now bending to build materials nature never made on its own. Light doesn't move the way you were taught. It moves the way quantum electrodynamics actually describes. And once you've seen that mechanism clearly, you can't unsee it. In something as ordinary as a glass of water on your kitchen table. If this is the kind of case file you want more of, evidence traced back to its original source, popular explanations tested against what actually holds up, subscribe for the next investigation, because there are a lot more everyday assumptions in science and history that deserve exactly this kind of scrutiny.